Yeah, the slides should be visible now.
Yeah, they are visible.
Okay. So before that, let me do one thing. You know what? Let me just stop sharing for a second. Uh, give me- okay. Yeah. So let me pull this up. So yes, over here. So I usually also run a demo for the algorithm parallelly. So where are we at shows? Yes, here we are. So you know what? Yeah, it's fine. Right. Try running this on. Yeah, sure, a CPU cluster. Why not? So at the start of this session, I've run an instance of the Shor's algorithm to factor the number 143. Okay, so it's not a very large number, it's not a very difficult number to factorize. Let us see what happens. So today I would like to like we'll be splitting our time half and half between the RSA crypto system and Shor's factoring algorithm. So typically, like Shor's algorithm these days is presented, you know, as a like generalized version of your, order finding process or the quantum phase estimation algorithm or so on and so forth. But what we will do is we'll try to observe the Shor's factoring algorithm from like the very basics. We'll start with arithmetic and try to grow towards the Shor's algorithm. And while we are doing that, I'll talk about what I think are the issues with the algorithms, what I think are the caveats that people should remember, and what kind of a threat such an algorithm poses to modern day crypto systems, and how severe the threat is. So before we begin, we have a small glossary of terms. Let me quickly run through it. A prime number, I hope I don't need to remind everyone what a prime number is, but nonetheless, a natural number p is prime if it is divisible by 1 and the number p itself. A number that is not prime is known as composite. Greatest common divisor is the largest number other than 1 that divides two given, or rather the largest number that divides both p and q. So GCD is defined typically between a pair of numbers. It can be extended to multiplets also, but again we can define it pairwise. So uh, if GCD of p and q is equal to 1, then p and q are said to be coprime. Now, then there is this notion of modulus, so or modulo. Modulo refers to the remainder obtained by dividing one natural number by another natural number. So when I say I'm dividing the number 5 by 2, then 5 mod 2 is equal to 1. 13 mod 5 is equal to 3. So it is essentially the remainder. Like when I try to divide a number, I have a dividend and a divisor, and I will get the dividend is equal to the divisor into quotient plus a remainder. That remainder is what we call the modulo. So from this, we can see that when I have, say, oops, when I try to define modulo m, then I know that this can take values only from 0 to m minus 1. Because if it's any value greater than m, then those m numbers can be taken and added to the quotient. Okay, so the remainder is always going to be a number in the range 0 to m minus 1, both are included. So this is a closed range. And the concept of modulo, like over here, I'm defining it for natural numbers, but we can extend it for integers. And, technically speaking, this whole modular relation can be extended to what objects which are known as modules, but we are not going to talk about that again. So then we have modular arithmetic. Now, what is modular arithmetic? So this is the idea. When I say, or rather, when I say I'm dividing natural numbers by a given number n, then it is possible for me to map all natural numbers to a finite set of numbers. Essentially, if I have A and N, like let me say A is congruent to B mod N, then this means A can be of this form. A can be of the form M times N plus B, where M can take any integer value. So for a given value B and N, I can have infinitely many A's. So essentially what I'm doing is I'm creating an equivalence class for integers based on my base of the modulus, which is N. Okay, so if we have any questions, you can also keep popping that in. Let me see. Let me keep that open as well. No questions yet. Good. Okay. So, and there are some rules. So if I'm saying, yeah, this symbol here, this is supposed to be read as congruence modulo or, congruent to B mod N. So you can just pronounce it as that. Essentially, what we are saying is this number A is equivalent to the modular class or modulo class B with respect to N. Essentially, this contains all numbers A such that when divided by N, they give a remainder B. Okay, so if A is congruent to B mod N, then A plus K is congruent to B plus K mod N. K times A is congruent to K times B mod N, and A to the power K is congruent to B to the power K mod N. So essentially, essentially, we can create a system of arithmetic out of this, and and that allows us to perform. Technically speaking, all finite arithmetic that we perform is actually modular arithmetic of one kind or the other. For instance, people who are like the present day ceiling is actually pretty high. But if anyone here is familiar with programming, say like in the late 90s or early 2000s, you will know that integers typically had a finite size. Like integers used to be 8-bit, 16-bit, so on and so forth. So they used to be relatively small numbers. So if perhaps in our calculations the number value exceeded the maximum allowed value for an integer, what we will have is what is known as an integer overflow, and the integer will kind of loop back into a smaller value. So this used to happen with signed and unsigned integers. That is also a direct result of the modular representation of numbers on digital computers. Okay, so the glossary is done. Now let us begin in earnest with the RSA crypto system. So the RSA crypto system is a public key crypto system. So the RSA crypto system is a public key crypto system. So what is a public key crypto system? So this is a system where the key has two parts. So typically when I have a crypto system, I have an encryption function and a decryption function, and a key may be different for the encryption and decryption function or can be the same, which is used to which is also given as an input for the function. So in a secret key crypto system or a private key crypto system, what happens is that the key is a secret. It is not to be revealed to the general public. It is not to be known to an adversary, and that secrecy is the foundation of the security of the system. Now, in a public key crypto system, what happens is, let us use the RSA crypto system as an example for the public key crypto system and see what the definitions are. So first we choose two numbers P and Q, which are prime numbers, and then we compute the number N, which is P times Q, and then we calculate this number called lambda of N, which is the LCM of P minus 1 and Q minus 1, and then we choose a number E, which is between 1 and lambda N, such that GCD of E and lambda N is 1. That is, lambda of N and E are co-prime. Okay, and then we calculate a number D such that E times D is congruent to 1 mod lambda N. So here we can define this new notion. So typically when we have real number multiplication or complex number multiplication, when I say the product of two numbers is 1, then we can say one number is the inverse of the other. The same definition holds for modular arithmetic as well. So when I say E times D is congruent to 1 mod n, then D is the modular inverse of E. Now N and E are made publicly available. Okay, so this N is actually known universally. N is the RSA number. So this is a universal constant. For different sizes, there are different RSA numbers. You can find a database of this on the internet. I encourage you to look it up. Typically, for a given size of a number, you'll have only one RSA number, maybe two for some smaller cases, but the larger it becomes, typically we will have one giant number. How big it is, we'll again see towards the end of our session. So N is the RSA number and the quantity E that we essentially chose. So this is the public key. The modular inverse of D is the secret key. Okay, so yeah, I'm sorry, I made a mistake. So this should not say N, this should say lambda of N. Yeah, I just realized something off. This is wrong. It should be modulo lambda of N, because the modulus here is lambda of N. Okay, what lambda of N is, we'll come to in just a moment. So now, what is the encryption function? So in a public key crypto system, there is one secret key which is kept with only the sender. The sender, sorry, yes. The receiver has the secret key. The public key is known to the sender. So the encryption can in theory be done by anyone in the public channel. And when they share the message, only the receiver who possesses the secret key can decrypt the message correctly. So public key is with any sender. So this way, for this reason, public key crypto systems are also known as asymmetric crypto systems. These are asymmetric crypto systems because the receiver and sender have like different information available to them and the mode in which they operate are different. So this is always with the receiver. Okay. Now, how is the encryption done? Now let the plain text be some number m. Okay. Then the number is encrypted. So let us assume that the message being sent is a number. Typically, any message can be mapped onto a number. So, that's a very valid assumption. So the number is encrypted by calculating the following quantity. You calculate C is equal to m to the power E mod n. N is publicly known, E is publicly known. So they just compute the exponent m to the power E mod n. And this C is the cipher text obtained from M. So now C is the thing that the sender has at their hand. Now this is sent to the receiver. Now how does the receiver decrypt this message? Now the receiver decrypts this message by just performing the following calculation. They will just calculate C to the power D mod n, and it is guaranteed to be M. Well, guaranteed with an asterisk, where we'll look at that just now. So this method was actually very widely used as a public key exchange system. So typically public crypto, public key crypto systems are, yes, technically it's public key crypto system. Key crypto system is, meaning the key is what is public. Crypto system itself is, just it's a mathematical object. So the key is public. Now, this technique that I've mentioned is reliable only when the message is between 0 and n. And for this technique to be practically secure, the numbers P and Q need to be very large. How large? Again, I'll come to it later. Additionally, P and Q, which I told are prime numbers. So in case, well, I'll say, so the distribution of prime numbers is actually not known. Like how they are distributed in natural numbers, it is not known. It is still an open problem. It is in fact widely believed that there is no pattern for the occurrence of prime numbers. One can give a probability of finding a prime number in a given like neighborhood, but one can never say when the next prime number is going to appear. So, but there are some algorithmic techniques for generating prime numbers. So those methods are not supposed to be used for RSA. For RSA, for this method to be really safe, these two prime numbers must be chosen at random. Like the choice should be really random. And that is why there are so few RSA numbers. And because finding this P and Q at random is actually very difficult, it is very time consuming. In fact, the very things that made RSA strong are the things that prevent us from using structured methods for choosing our prime numbers. Because if they were chosen using a structure, then the adversary might be able to exploit that structure to mount an attack on this crypto system. Now, this is the RSA crypto system. So this number M has been transmitted from the sender to a receiver. And for now, I am saying that only the receiver who knows D is the secret key. It's only with the receiver can find out what M is given C. For everybody else, C is going to be just some random number. Okay. Now, why does RSA work? Now, RSA works because of the properties of what is known as the modular exponent function. Essentially, this thing that I've shown here. So this is the modular exponent. Yeah. So the modular exponent function. So let me. Okay, so they can only post questions, right? I can't have a back and forth here. You know what? Some of you can actually type the answer in the questions itself. So is the exponential function a periodic function? Can someone say, give a yes or a no? Something? Anything?
Yes, somebody shared. Yes, sir.
No, that came a bit before. Yeah, now, yes. I'm seeing the other yeses. Yes. What's the receiver? Okay, so there is a question. I will come to this later. Muhammad Kamal, I'm unable to read your full name. Sorry about that. So yes, the exponential function is actually a periodic function. So to see the periodicity of it, one actually needs to move to the field of complex numbers. In real numbers, well, it is just a monotonically increasing function. But in complex numbers, both the exponential function and the logarithmic function become periodic functions. And at the modular level, this periodicity again reappears. So these are actually periodic functions for all natural numbers a and nx. So if I were to perform fa of x, which is given by a to the power x mod n, then for all natural numbers a, n, and x, this is a periodic function. If a and n are co-prime, that is if GCD of a and n is equal to 1, then there will always exist an natural number r, a set of natural numbers r, such that a to the power r is congruent to 1 mod n. Essentially, if I calculate a to the power r and divide it by n, it will give a remainder 1. So this statement, this is what is known as Euler's theorem. There is a previous version of this theorem which proved it for all prime n, so that is called the Fermat's little theorem. Euler generalized the result to any general natural number. Okay, so the smallest value of r, so essentially there can be many values of r for which this is true, and because the function is periodic, you can also see that these will actually be integer multiples of some fundamental number. Okay, so what I'm trying to say is, let me say, let me say for some r, I have a to the power r is congruent to 1 mod n. Then a to the power r plus 1, if I increase r by r plus 1, what is going to be the value? Just to revise, we have this here. So if A is congruent to P mod n, then K is congruent to KB mod n. So I can use the same result here and say this will imply automatically that A to the power R plus 1 is actually congruent to A mod n. So what has happened is the cycle is beginning again. So if A to the power R plus 1 is the same as A to the power 1. So after R, I start at 1 and again go to another R, and then I will start at 1 and go to another R values. So the smallest value of R is, the period, or also known as the order. So that is the formal term here. So it's called the order and the square braces. So this is called the order of the number A. So this has a important consequence in modular arithmetic. In this case, the quantity lambda of n is actually the smallest such value. So this quantity that we calculated here, LCM of p minus 1, q minus 1, if n is a product of two prime numbers, then we have a ready-made formula to calculate it. So that is lambda of n. And this number is called the reduced totient function, also known as the Carmichael totient function. So this, for any number that is a product of two primes, it is defined as LCM of p minus 1 and q minus 1. There is a general definition for any natural number, but that is not our primary focus here, so we shall not discuss too much about that. I encourage you to again look these things up. Okay. Now, assume that M is co-prime to the RSA number N. The message. Oops. Yes. Yeah. So let us assume for now that M is co-prime to the RSA number N. Then the ciphertext can be calculated as C is equal to M to the power E mod N. And then during the decryption process, we will calculate C to the power D. Now C to the power D will actually be essentially, I know C is congruent to black blends. So if I say C is congruent to M to the power E, then C to the power D will be congruent to M to the power E whole power D. Again, both of these are mod N. So what we have is M to the power lambda of N. Okay, so or to be more precise, it is going to be some k times lambda of n plus 1. Now we know that any integer raised to this power will always be this quantity is always going to be 1. That comes from Euler's theorem, because the exponential function, remember, has a fundamental period. Now, since it has a fundamental period, any m to the power lambda is going to be congruent to 1 mod n. 1 to the power k is again congruent to 1 mod n. So I have k plus 1. So that is another factor of n. So I will get m mod n. So the number m is obtained. Now, additionally, RSA also works if m is not co-prime to n. But again, I'm not going into the proof for that. The proof for this is obtained using what is known as the Chinese remainder theorem. So this is a theorem about a system of equations in modular arithmetic. So using that, we can say that even when m is not co-prime to n, the RSA crypto system works. Okay, so this is the reason. Ultimately, the reason why RSA works is is Euler's theorem, or further variants of the Euler's theorem. This is the backbone of RSA. And given, given this ciphertext, if I calculate m to the power e mod n, and if I give c, it is actually difficult to find what m is. We know e is publicly available, but we cannot find m because I've already reduced it to modulo n. So I know for a fact that 0 less than equal to c less than n. Like it goes up to n minus 1. So I know that c is always going to be in this range. So this is a many to one function. Multiple values of m can end up giving me the same value of c. So this does not have a very well-defined inverse. So modular exponentiation is also what is called, where are we? Yes. So, oh no, here. Yes. So this modular exponentiation function is one example, although now it is a defunct example of what is known as a one-way problem, wherein calculating the function is relatively easy. In fact, performing this is actually very efficient. Like this almost runs in what, logarithmic time or maybe order log time. So it is actually more efficient than linear time. So it runs sublinear complexity, but calculating the inverse is near impossible. To calculate the inverse, I need to know some things. I need to essentially, the thing I need to know is D. So I need to know the secret key. But so that is where we have this notion of one-way problems, and every public key crypto system, like even before that and since, has a hard one-way problem at its heart, or at least a problem that is considered to be hard at its heart. Okay, so yeah, moving on. So now what does it take to break RSA? So the only publicly known parameters are n and the public key e. Everything else is a secret. Now the only way to know anything further is to know lambda of n, which is LCM of p minus 1 and q minus 1. Because once I know lambda of n, I can calculate the secret key. If I give lambda of n and e, I can calculate d. Once d is known, then anybody can just take the ciphertext and extract the message out of it. But lambda of n is defined as LCM of p minus 1 and q minus 1. So in order to find lambda of n, I need to find out what p and q are. So the challenge to break RSA is to factorize the integer, the RSA number. So the only challenge in completely breaking the RSA crypto system is integer factorization. Now, sources vary. Now, some people will say that integer factorization is a hard problem. Some people will say it is not. I lean on the latter side because, yes, now there does not exist an algorithm that is polynomial time in log of n. So if I need to factorize an integer n, capital N, then, or rather, why you say capital N, I can say small n itself, because that is what we are working on. That is what we are using here. So log n gives us an idea of the number of bits in the number. So it essentially gives me the size of the number. So there is not a polynomial time algorithm in the size of the number. But that itself does not make it a hard problem, because, again, one more question to the audience. Let us say I'm writing the binary expansion of a number. If I tell you that the least significant bit of that number is 0, can that number be a prime number? I hope you understood my question. If I write the natural number as the binary expansion? Yes, I have one answer. Well, technically there is one number where it is true, which is 2. 1 0 is prime, but that is the only number. Because if the least significant bit is 0, the number is even. So 2 is always a factor, and 2 is the the first prime number. But other than that, every other number is an even number. Yes, except for 2. I know for a fact that they are composite. So expecting an algorithm in the size of the bits, polynomial in the size of the bits, is actually not fair. Because for half of all integers, if I just look at the LSB, I can say whether it is composite or not. For literally half of all integers, every alternate number is an even number. So this definition is actually not very strong. Technically speaking, we have an algorithm that is cube root of n log n to the power 2 by 3. Yes. So, yes. So we have an algorithm with this kind of a complexity for factorizing integers. Technically, this is not super polynomial in the integer itself, because you see it is cube root of n. It is actually sublinear. Technically speaking, if I'm given a number n, what can I do? I'll take all numbers less than it and divide it to see what whether it is co-prime to a number or not. Whenever I'm seeing that there is no co-prime, like when I'm seeing that there is a GCD or something, I know that okay, which direction to look for a factor in, because a GCD will always contain at least one factor of a GCD between two numbers, if not one, will always contain at least one factor of the number. In this case, I know n has only two factors. So if I find another number with whom the GCD is not equal to 1, then that number definitely contains a factor of my number n. So in linear time, by just performing the GCD algorithm, which is your Euclid's algorithm, which is again a very efficiently implementable algorithm, I can solve the factorization problem. Now, how is RSA made hard? RSA is made hard by making this number so large that it is intractable to calculate. So this is technically not a hard problem. Like if I go to the core meaning of hardness, RSA technically is not a hard problem. The algorithm to solve integer factorization and the fastest known algorithm has this kind of a complexity. It's cube root of n times log n to the power 2 by 3. So it's actually pretty, it scales reasonably well. As long as one is willing to ignore the definition that all algorithms need to be polynomial in the size of the integer. Okay. So when we choose a large enough number, this will become extremely time consuming. Now, let us see. Now let us try to factorize the number 143. Now I'm giving a classical factorization algorithm. Yes, we are on good time. We've just cleared the half an hour mark. So yes, so now how do we go about factorizing numbers? Like, of course, there are classically, so this algorithm is known as the, so this stands, this is the GNFS algorithm, or the generalized number field seal. So I'm not writing the whole thing. So this is the existing classical algorithm for factorizing large numbers, and it has an asymptotic complexity of cube root of n multiplied by log n to the power 2 by 3. Now we are not going to follow the GNFS logic. We are going to come up with our own, homebrewed strategy. Or essentially, this is what Shor figured out. And of course, like in a minute, I will say what was figured out. So now let us consider n is equal to 143. Now I'm choosing A to be 21. Now 21 is co-prime to 143. That can be readily seen, readily observed. Now what I'm doing is I'm calculating the following. For every value of r, I'm calculating 21 to the power r mod 143. So 21 mod 143 is 21 because 21 is less than 143. 21 square is 441. definitely greater than 143, but the modulus will come out to be 12. And then the cube will give me 109. The fourth power will give me 1. Then I will again begin at 21, 12, 109, and again 1. So this cycle will keep repeating over and over and over again. So from the previous table, we can see very readily that lambda of 143 is 4, because this seems to be the smallest number for which the, like, after 4 orders, I am arriving at 1. So that is the definition that we had. So lambda of n, lambda of 143 should be 4. Now this implies that 21 to the power 4 should be congruent to 1 mod 143. Essentially, when I divide 21 to the power 4 by 143, I will get a remainder of 1. What this means is, just to be clear, 21 to the power 4 is equal to some k times 143 plus 1. Now what I'm going to do is I'm going to take the 1 over here to the left hand side. So 21 to the power 4 minus 1 is equal to k times 143, which means it's a multiple of 143, which means the remainder is 0. So that is congruent to 0 mod 143. Now 21 to the power 4 can be written as 21 squared minus 1 into 21 squared plus 1. These two numbers are congruent to 0 mod 143. Now, what am I saying? I'm saying the product of 21 squared minus 1 and 21 squared plus 1 is a number that can be divided by 143. It's a multiple of 143. Now, then we need to ask a question. Does 143 divide 21 squared minus 1? The answer is, you can verify, no. The two numbers are, are they co-prime? No, of course they're not co-prime. Yeah, this does not divide this. Yes, like it's not equal to 0, not congruent to 0 mod 143. 21 squared minus 1 is also not divisible by 143. Now, for the above statement, for this to be true, now see, this number is k times 143, which implies the factors of 143 need to appear in the factors of this number and this number. Now I know 143 individually does not divide 21 squared minus 1 and 21 squared plus 1. So that means the factors of 143 should, one of them should be here, the other one should be here, because there are only two factors. So what I'm going to do is I will take 21 squared minus 1 and calculate its GCD with 143. So that is GCD between 440 and 143. We use the Euclid's algorithm and we will find out that the GCD comes out to be 11. So 11 is one factor. The second factor, since I know there are only two factors, I will just divide 143 by 11 and I will get 13 to be the second factor. Of course, the GCD evaluation can be done using the extended Euclidean algorithm. Now let me take a quick 1 second break and oh God, I don't know what difference this makes, but let's see. It's still running. Really? Okay. Yes. So yes, it shows a equal to 123 and it factorized and gave me the factors 11 and 13. So whatever Shor's algorithm has been defined on this platform, it is able to factorize 143. Okay. So I just ran this program here and I've shown it. Don't worry, there is going to be more in the demo. So we'll come back to it in just a moment. Now we come down to Shor's algorithm. So the previous method that we described, whatever we did here, tabulate these values, observe the periodicity. Once you observe the periodicity, perform this kind of a split, analyze that the number is neither of the factors are not divisible by 1 for like the base, the modular base, and then evaluate the factors via GCD calculations. So this is Shor's algorithm. Now, Shor's algorithm leverages quantum parallelism. So why is Shor's algorithm so special? Because it is a quantum algorithm that leverages quantum parallelism. Parallelism essentially implies that time evolution is linear in quantum mechanics to calculate all the values of fa of x, the modular exponent, for a large number of values of x. Now see, over here for each of these things, I had to calculate the modular exponent. I actually wrote a small program to do that. There are ready-made library functions available for that, but just for fun, I wrote my own small script over there. So quantum parallelism is leveraged to calculate the value of the exponent, the modular exponent, the value of the modular exponent for multiple values of r. And then I have a quantum state that contains all these values of, essentially, I will have, what I will have is something like this. So if I have this here, so look at this, I have 1, 2, 3, 4, 5, yes. Let me take up to the value 6. So what we will technically have when we perform Shor's algorithm is we will have a resultant state, KETSI, that will be something like this. It's going to be KET1, KET21 plus KET2, KET12 plus KET3, KET109, oops, 109, and KET4, KET1, KET5, KET12, KET6, sorry, not 12, what did I say? 21. And then KET6, KET12. So to write this, like what I'm saying here is these will all be like binary representations. Okay, so these will all be binary representations of these numbers. Like I know this number is always going to be between 0 and n-1. So if I have ceiling of log n qubits for this, I can represent all the numbers over here. If I have whatever the range of r I want to test, I will take those many qubits here. So these are all like binary representations of those numbers. And I will have a state like this. Of course, there is going to be, and so on. There is going to be an like square root of 2 to the power r, whatever upper bound r I have for calculating this exponent. Okay. I just realized some of my writing is clipping past the slides. Yes. Yeah, I'll do that at the end. Okay. So this is a normalized state. Now, for 21, I could actually just look this table up and find out the order. Now, what will happen when I have a very large unknown number? I don't know what this periodicity is. The periodicity may be so large that I cannot repeat this calculation classically, individually, one by one. So now I calculated for a very large number of hours, hoping that the period has occurred within the range that I'm considering. And then, how do I find out what the period is? Can anyone give me a guess? If I have a state like this, what can I do in quantum computing that will allow me to find the periodicity of this sequence? Classically or quantum, using classical or quantum computing, if I have a sequence and if I want to find the periodicity of the sequence, the best known method is actually Fourier transform. It's Fourier analysis. So we use quantum Fourier transform to find the period. Once the period is known, we will use that to classically find the factor. So the Shor's algorithm does not output the factor. Shor's algorithm, in fact, will only give us an estimate of the order. Why is it an estimate? You'll see just now during our demo. It will give us an estimate of the order. Using that estimate, we should be able to guess what could be the factors. Do not guess. We should be able to evaluate what should be the factors using classical techniques. So the Shor's algorithm is a hybrid algorithm. The answer that we desire is actually obtained by us using classical means. Now, what do we need for Shor's algorithm to work? First, I will need a number A that is co-prime to my number n that I want to factorize. So first I need to find a number A that is co-prime to n. Second, remember the trick that I did here. I wrote 21 to the power 4 minus 1 as 21 squared minus 1 and 21 squared plus 1. So the second thing that is required is the modular exponent r must be even. So it need not be like, it should be an even value. The thing that I obtain should be an even value. Only then can I do this split here. So when the modular, like the order, the periodicity is even, then what happens is the following. So essentially, what I'm saying is, let me just write it here. So R should be equal to 2k. Essentially, a to the power r congruent to 1 mod n implies a to the power k whole squared congruent to 1 mod n. So this actually has a very fundamental implication here. So first, this kind of an expression. So people here who are familiar with number theory will know that this kind of an expression where I'm writing some number, p squared is congruent to some q mod n. So this expression is what is known as a quadratic residue. These are objects that have been studied for a very long time. Like quadratic residues have been of interest for people since Legendre. So all the way till Gauss, and even to this day, there are many open questions in quadratic residues. So this is what is known as a quadratic residue. So first and foremost, I will need a to the power r to be a quadratic residue. I will need a to the power r to be a perfect square. It should be a to the power k squared. Now thinking in modular arithmetic, if a to the power k times a to the power k is congruent to 1 mod n, then this further implies a to the power k is its own modular inverse. So like a to the power k mod n is going to be some number, but if I multiply another a to the power k to it, it comes to 1. So a to the power k inverts itself. And by that definition, it becomes a quadratic residue. Okay. And that alone is not important. Another final thing, going back to the example that we solved, both of these factors should not be divisible by n. So essentially, a to the power k plus 1 and a to the power k minus 1, minus 1 should both not be divisible by n. Oh no, should be written the other way around. It's a divides b. So statement is n does not divide a to the power k plus 1 and n does not divide a to the power k minus 1. So these three conditions should be satisfied for Shor's algorithm to be successful. Are the slides not visible? I'm sorry, I didn't notice the comment. Sumit,
oh no,
it's
visible.
Okay, then it should be some issue up there.
Yeah.
Okay. Yeah. Okay. So these are three conditions that should be met. If these conditions are not met, then Shor's algorithm has failed. Then I have to go choose another A and then repeat the process. Now, what? Let me open this window. Now let me zoom in and let me switch to dark mode. And now the text should be reasonably visible. So you see the program that I ran for factorizing 143 took A is equal to 123 and discovered 11 and 13. But this will not always happen. For instance, if I go to the composer, I should have my older jobs also. Let me take this one here. Yes. So you see, it took A is equal to 30 and got, again, I tried to factorize 143 only. So just 1 second to go up. No, where is the code? Yes. So I was trying to factorize 143. So first it shows is actually a poor number because it's a multiple of 10, like it has several problems in choosing a number that's a multiple of 10 because it has two very prominent prime numbers in it, 2 and 5. So it's a problematic choice. So what happened was a trivial solution was found. What is a trivial solution? A trivial solution is when either one of these conditions fail. When either one of these conditions fail, I have nothing more, no more information. So I need to abandon my algorithm. So A equal to 30 was a bad choice. Then they chose A equal to 9. For A equal to 9, you will actually get an odd number as the order for 143. So once, oh no, yeah, you'll get an odd number, yes. So the algorithm failed again. Third attempt, it took A equal to 87. Then it could factor. So Shor's algorithm is not a guaranteed success algorithm. We need to find a proper A. Okay, so now let us remember these three things. So first, I need that A should be co-prime to N, and I need R to be even. So typically, theoretically, A is chosen from this interval, or rather, let me write it like this: N squared to N squared. This is a region where I can say with a high degree of confidence that any random number that I choose here will be co-prime, and I can also be reasonably sure that the order that I evaluate will be an even number, that it will be a quadratic. I could find a quadratic residue in this interval. Now remember, if n is an L-bit number, if this is an L-bit number, how many bits is n squared? Approximately. So this is actually a 12-bit number. And this is 12 plus 1 bits. So this is actually the good region to look for numbers. And once again, I will go back to the previous run I performed. First value was 30 because it's nowhere near the square of 143, which is why it's a bad choice. A is equal to 9, an even smaller number. But in the defense of this program here, I chose 21 in my demonstration to factorize it. 21, also doesn't fit that. Now, why isn't this programmatic implementation taking the theoretical recommendation? The reason is, if it shows those larger numbers, the classical computation will actually take significantly longer. The classical computation required to implement the quantum oracle, the classical computation required to design the circuits will actually take longer. Now, what does that mean? That is what we are going to look at, as the title of the slide says. So let us consider a simpler problem. Let us consider n equal to 15. Now 15, is a very special number. So what are the specialities of 15? 15 is actually the first number factorized by Shor. By Shor's algorithm. So this was done I think in 97, approximately 1997. Here, like, give or take 1 or 2 years. And this was done on an NMR based quantum computer. I don't know how many of you are aware of this. Like, how many people, just out of curiosity, I'm asking, how many are aware that NMR based quantum computers used to be a thing? Yeah, don't seem to see many thumbs ups or many acknowledgements. Yeah, it's a relic of the past because they have very poor scaling. Although NMR-based quantum computers have exceptional coherence times. Like, they have coherence times that actually last. Yeah, yes. So NMR stands for nuclear magnetic resonance. So this used to be, not used to be, it still is a technique for analyzing chemical molecules. It is used in a wide variety of fields, starting from basic chemical analysis to chemical forensics, medical research. Essentially, your MRI is an NMR machine. When you perform an, I see a hand raised. If you have any questions, please post them on the Q&A. So when you have your MRI done, what it's doing is actually performing the NMR of the molecules in the tissue that is being scanned. Any anomalies can be traced by looking at the different nuclear, like the nuclei of the atoms present in the organic molecules. So this was done on an NMR-based quantum computer, and it used 7 qubits. So this was done using, the implementation was done using 7 qubits. But performing quantum computing using an NMR-based system is actually very difficult because you cannot get arbitrary internuclear interactions. It is highly contingent on the distance between them. Any stronger magnetic fields might end up disrupting the other qubits. So it has plenty of scaling issues. Okay, so any plus software needed for this experimentation implementation? Like the one that I'm showing here, all of the software backend is handled by the service provider themselves. So you can actually even import your QuickSkit or let me go to the composer. Like they support these languages. They support QuickSkit, CUDA-Q, QEST, QLAX, and so you can even compose circuits and it will generate things. I hope this is what you're asking. So you can get, like, this supports all the languages in it. You don't need anything more than this. Like they even have a decent enough backend for running your Python codes, and they also give their own hardware providers for simulations. If you want to do quantum stuff, you can actually run it on any either QuickSkit, or I think Circ also offers some machines. So you can use them using your account and your user token to run your jobs on that. Okay, so back. So this was factorized. This was the first number to be factorized by RSA. Now what I'm going to do is, now see, it's 7 qubits. Now remember, over here, this should contain log n qubits, right? So this should contain, like, whatever my value of n is, it should contain log of that. Now what is log of 15? Log to the base 2. Okay. Whenever I say log, yeah, I should actually write that somewhere. Where did I write log? Over here, yes. So I should clarify that this is log to the base 2. I mean, other logarithms also give me the same value, but it is scaled by a numerical factor. Let us not deal with that. So log to the base 2 of 15, the floor of it is actually equal to 4. So I need 4 numbers to represent the modulus itself. So I have 3 qubits left for the choice of A. So A can only be between 0 and 7. So this is actually a very, poorly implemented Shor's algorithm. This is not implemented in accordance to the theoretical recommendations. So now how do we go about constructing it? So what we do is the following. Use layout. So essentially what we do, so in our case, what I'm going to do is n is equal to 15. I'm going to choose a is equal to 2. I'm cheating here. I know why a is equal to 2 is a good choice. And obviously I know what the factors of 15 are. But nonetheless, I'm just going ahead and choosing a equal to 2. Now what is 2 to the power 1? It is congruent to 2 mod 15 because 2 is less than 15. 2 to the power 2 is congruent to 4 mod 15. 2 to the power 3 is congruent to 8 mod 15. And 2 to the power 4 is 16, which if I divide by 15 will give me a remainder of 1. So it's congruent to 1 mod 15. So 2 is actually a very convenient choice. So, and so on, I can keep defining it ad nauseum. Okay, so now what we need to remember is we need to create a function that takes R and calculates FA of R according to the old notation that we used, FA of R. Takes R as an input and calculates this. Now, if we are thinking in terms of quantum oracles, so I hope you are familiar with Boolean function oracles. Oh yes, for research purposes, you can use that. I mean, they encourage you to use it for research purposes, by all means. I mean, partially I'm also promoting that software because it is completely indigenously made. I know the people who have made it, like it's made by CDAC, like several CDAC centers. So it is made by an Indian government laboratory. I know the people who made it, and I've worked with them on several occasions, and I really like it. Like for my teaching purposes, I don't do much of serious research on the programming end. Most of my research work is on the theory side of things. But I mostly use it for teaching, and for my teaching purposes, it's a very good tool. I don't see why it will not be a good tool for research purposes as well. Sumit should have shared the link to that website. The registration and everything is free. So you are, I encourage everyone to join it and use it. So, and there are no restrictions. So even our foreign attendees are also welcome to register and use it for their purposes. Okay, so essentially I will have ket R and ket 0, and I will have UF, which will give me ket R and ket F A of R. So this is the bit oracle implementation. So this is the bit oracle implementation. Or alternatively, what can I do? I can create the other version wherein I have, let me call this UF prime. No, F prime is not a good sign. Let me call this UP of F, wherein I will have e to the power I FR A, sorry, FA of R, yeah, FA of R times keta. So this is the face oracle representation of the function. I can create either the bit oracle, or the face oracle representation of the function. Yes. Okay. Let me again, since we have enough time, let me. Yes. Briefly talk about QDiverse. To register to the platform, things are free. If you need more credits, they keep conducting activities every month or so. If you take part in them, you'll get like some 200 to 500 credits. Like you don't need to actively spend money to get credits on that. Like the credit system there is only to encourage engagement. Okay, so every month or so they will have their workshops, so you can just enroll, attend, and you'll be given more credits. If you need more credits, you can also contact them. You can work out some procedure with them also. I'm sure they will be happy to oblige. And the attendance code question has been answered. So yeah, I've spoken about the credits and this. There is one more question in the beginning. I promise you I will go to it in just 1 minute. So now, first, using this function, I need to create this oracle for my quantum circuit. And then, we will start with the processing. So let us take n equal to 15 and a equal to 2. How do these oracles look like? Now we go to the active demonstration. Yeah, let's set this to 6 and 6. So whatever they did with 7 qubits, I managed to implement it using 6 qubits. Okay, so let me also get rid of this, get rid of this. Yes. So I have this gate over what? Really? Why is this only 5 qubits? Oh god, it has been truncated. Q2, Q3, Q4. No worries. It's fine, it still works. Yeah, so there is an internal optimizer that just truncated my unnecessarily large. Can I just give that? Can I change? Yes, I can. Yes. So A, B, C, D. So A and B, let it be Q0 and Q1. I just need to make D as Q5. Yeah. So, nothing much happens here. So you'll see what happens. So now this circuit will look something like this. It's going to be a whole bunch of, phase gates, X gates, and Toffoli gates. You can implement it using these 3 gates alone. And now how I constructed this oracle, again, I use some hindsight to construct this oracle. But notice that even for n equal to a equal to 2 and n equal to 15, this circuit is not very straightforward. Like, yeah, I'm using some symmetries to make it look simple, but the truth is the design of such a circuit for an arbitrary n and arbitrary a is actually pretty difficult. Okay, so that and then so you can see that initially nothing is happening. So what I'm going to do is now I need to generate this over all possible values of R. Now, okay, can I zoom further in? So I hope you can see this. All these probability values are all, let me make this a state vector. Yes, this is better. So now notice there is a temperature plot for the angle. You can see that the pattern repeats every 4 times. I have a green bar here. I have a green bar exactly 4 after that, exactly 4 after that, exactly 4 after that. So this tells me that this periodicity is being followed essentially. Just to be clear, just to be clear, if I were to just get rid of all of this and write the next 4 values just for the sake of completion. So 2 to the power 5 will be 32, which is 30 plus 2, so that is 2 mod 15. 2 to the power 6, 64, which is again 4 mod 15, 60 plus 4, and 2 to the power 8, sorry, 7 is 128, which is 125, which is 127 plus 1. So, sorry, 120 plus 8. So that's going to be 8 times. 8 times 8 mod 15. And then 2 to the power 8 is going to be 256, which is going to be 255 plus 1. So this is what is happening over here in the faces of my qubit. As you can see, I hope the colors are, there is enough contrast on your display. Can I zoom in further and make this? For some reason, the y-axis seems to be rescaling, no matter how much I zoom in. Yeah, it's still the same size, unfortunately. So as you can see, the amplitudes, yeah, I will use, yes, the amplitudes show a pattern of 4 periodicity. But again, this is the state vector from the simulator. I cannot see the state vector. What I will see when I measure this are these output states with a certain probability. So now all states are equally probable. Like they all have like 3.13, 3.13, 3.13 all across the board. So I'm getting nothing from this. I have implemented the exponential, the modular exponential function. So that is what MEX stands for, modular exponent. I'm only allowed to use the 3-letter code for my gates. IQFT and QFT are privileged. So MEX is that. Now, to find out the periodicity of this. Now remember, when I measure it, I will have no idea about the periodicity. Now to find out the periodicity, let me bring in the, you know what, let me just do the Fourier transform. I don't even need to do an inverse Fourier transform because they're both one and the same. And over here, so these are predefined circuits. So I just need to say over which circuits, which qubits I need to perform the IQFT. So this bottommost qubit is what I'm using to calculate this phase factor. So that is not a part of my circuit technically. It starts off as KET0 and ends as KET0. Okay, so I can neglect it. Now I have performed the Fourier transform. Now look at what happens to the graph. As you can see, now only 4 possible outputs are appearing, but this is the probability distribution. What happens to the state vector? Now you can see that I have one peak occurring at all zeros, another peak occurring at, so essentially this is supposed to be read from this end. So they use the, I think this is called the little endian notation. If I'm wrong, it's the big endian notation. So this corresponds to A equal to 4. This corresponds to A equal to 8. Sorry, R equal to 8. And this corresponds to R equal to 12. Sorry, R equal to 6. Yes. So, no, 12. Yes, it's actually 12. Yes. So it has a period. Oh, yes. The last one here is actually the superfluous 0. It's supposed to be read from this side only. So this is 4, this is 8, and this is 12. 8 plus 4, 12. So in the previous sequence, let me quickly remove this. Scroll down. See, this is a sequence of periodicity 2. But technically, it also has periodicity 8. Because if I move 8 positions from here, I'm again seeing green. And because I've measured this for I've actually measured it for 32 possible values, there is also a periodicity of 12. I can jump ahead 12 positions. So that is 1, 2, 3, and 1, 2, 3. So I also have a periodicity of 12 here. So these, essentially any integer multiple of 4 is a valid period here. And since I've observed it only up to 32, I'm getting the, now let me bring back the Fourier transform. You know what, for variety, let me use the inverse Fourier transform just to make a point. I may edit it to include all 5 of these. Again, have the same. Only the angles have changed. Otherwise, nothing else has changed. So the same amplitudes will be obtained. So I can get a value of 0, I can get a value of 4, I can get a value of 8, I can get the value of 12. So these are the possible periodicity values that this Fourier transform will give. Now, when I measure it, you can see that on 0 state is the majority vector. Like that is the vector that I will measure with the highest probability. And that actually does not give me any information. It tells me R is equal to 0. That is invalid. So I did some cheating to create this oracle. So because of my shortcut, I could not eliminate this vector. To eliminate this vector, I need one more qubit, which is what the people who factored 15 using the NMR quantum computer did, because they also did the same mathematics and they knew that the 0 vector is very problematic, so you need to get rid of it. They would have gotten only these 3 vectors. I didn't bother doing that. So, I got the 0 vector. Now, when I perform a measurement, I will get 0 with the highest probability. In fact, it's 75% probability. I will disregard that. The remaining 25% of the time, I will get 8, 4, and 12. 12 is the least, 8 is the most, and 4 has a 5% probability. So when I get the number 8, should I assume that the order is 8? The answer is technically yes. Even if you assume the order is 8, you will double reduce and arrive at the 4 case. So typically what happens when we are performing Shor's algorithm is, I will create this circuit and then I will perform the measurement. And one of the measurement values will correspond to the period. So if I'm getting a number 8, so ideally I will perform enough measurements so that all possible values occur at least once. If not, there are other methods. There is the method of continued fractions, which will also allow us to estimate the period. I'm not going into the details of that. I will recommend for people who want to learn the continued fraction method, please refer to Nielsen Chuang, the chapter on quantum Fourier transforms, algorithms based on quantum Fourier transforms. So there it is explained in detail, including the complexity of the process and how to mathematically evaluate it. It's a classical process. So I will get one of these 3 values, and from these 3 values, I will find the period. And after finding the period, I will be able to factorize 15. Now let us finish the whole thing and bring it home. Now from this, I have found that R is equal to 4, which implies 15 divides 2 to the power 4 minus 1. 2 to the power 4 minus 1 is 15. So that's obvious, which implies 15 divides 2 to the power 2 minus 1 and 2 to the power 2 plus 1. Now you know that this is 3 and this is 5. So for this case, just factorizing to the power 4 minus 1, again, I'm not factorizing 15. I'm just using the property of polynomials. I'm just using the property that a square minus b square is a plus b into a minus b. I just arrived at the 2 factors. Without performing factorization, I've pulled out the 2 factors. So this is how the Shor's algorithm runs. So now I will take some questions that are present here. Yeah, so at present, okay, you're using IBM Qiskit for the lab course. If you want to switch to QUniverse, I will encourage you to just write a mail to CDAC. Like the contact details are all available on that QUniverse webpage itself. You just write an email to them and tell them that these are your needs. I'm sure they will be happy to oblige and provide you with the necessary free registrations, or if there is a cost or stuff, it shouldn't be too much, because this whole thing is funded by the government in order to provide free what to say, like a very low cost learning alternative for the students. And using QUniverse, if they want to run anything on Qiskit, they can just use their Qiskit account and log on to that and run the simulations on actual machines as well. Now, of course, this process cannot be fully free, because ultimately they have machines which are running the programs that students are running. So there will be a nominal cost, but I'm sure it will be significantly cheaper corresponding, when comparing to running things on IBM Qiskit or stuff like that. Because I know how much IBM costs for professional level access to machines, and it is not, I mean, it's a lot. Like, it's not little by any means. So I would encourage you to contact CDAC and, yes, you can. If you have an IBM account, again, QUniverse will not provide you access to the higher level, the restricted GPUs. If you have a free account, then you can only use the free QPUs of IBM. If you have a privileged account, then you can, you can take the open access QPUs. Yes, that can be accessed. Now, if you're already paying money to IBM, then you can use it kind of, what is the thing? It's a bundle subscription kind of a thing, where you can access all of them using QUniverse. So yes, you need to add your API. Yeah, it is free. Yes, like at least the basic features of it are free. You just need to request access. They will, grant you a, like, make a username and password and request access, and you'll be granted an account. And after that, there are tutorials to walk you through everything, and it's basically just is slightly more, uh, what is the word, neophyte friendly IBM Q. Like, IBM has a lot of information on the back end, but the front end is usually pretty barren. Here, the back end is so. It's like constantly evolving, but the front end has enough information, enough tools. Like IBM, over the past years has retired its simulators, like its server-based simulators. So now, if you need to use the IBM simulators, you are forced to run things locally on your own machines. If that is not a viable option for you, then you're welcome to use QUniverse. Okay, so that. Yeah, so yes, they have a webinar series. So if you participate in the webinar series, you'll get some extra credits and things like that. Funnily enough, this very lecture that I'm giving you 1 month ago, I gave in the QUniverse webinar series also. So you can also see another copy of that. So yeah, now some interesting facts. How serious is Shor's algorithm to the RSA crypto system? Now, I've shown you how numbers are in general factored. Yeah, I have 5 more minutes. So yes, if you have any questions, please start dropping them in the Q&A. I'll take them and finish off this session. Okay. So now we've seen how numbers can be factorized by the RSA, the Shor's algorithm. So RSA is in threat. Similarly, a Shor-like process, essentially a period finding technique, can be used to break another public key crypto system, the Diffie-Hellman or the elliptic curve Diffie-Hellman crypto system. So that was another public key crypto system that existed well. Diffie-Hellman can be broken using Shors. Elliptic key Diffie-Hellman was actually broken using classical means. So that's what I'm coming to now. What about